Hello. In this video, we study spaces associated to a matrix. For matrix, we have row space, column space, and null space. Okay. So suppose that you have some matrix A, and you can write A11, A12, and so on, A1n, A21, A22, A2n, and AM1, AM2, and AMN. So this matrix has m rows and n columns. Okay. So if you just consider rows, right? So you have m rows, and rows are in space Rn. You see, because each row has n coordinates, right? N numbers, n entries. So let's say, yeah, that is A11, A12, so on, A1n. Okay, and you have m rows, AM1, AM2, and so on, AMN. All these rows are vectors in Rn. Why columns are vectors in Rm? Why? Just like the first column is what? I can write in the transport form, okay? I have A11, A21, and so on, AM1. That is the first column. And so on, you have A1n, A2n, and so on, AMN. You see? So you have n columns and m rows. They are in different spaces. You see, they are in different spaces. Now, rows are in Rn and columns are in Rm. We know subspaces generated by vectors. In this case, it has some meaning to study subspaces generated by rows and columns. And they are called row space and column space. Okay, so from here I have row space and column space. And of course, we are interested in basics and dimensions. Okay, you see, basics or dimensions of row or column spaces. And the null space is the following space. The null space is what? Is all x such that ax equal to 0. So basically, what are they? From the definition, you would think that, yeah, actually they are in Rn, right? They are in Rn. Is it correct? Means, n, and not only that, not only in Rn. Actually, this is the solution set or the solution subspace, right? The solution space of the homogeneous system. Right? Ax equal to 0. And we know that, the solution set of homogeneous system Ax equal to 0 is a subspace. So I can write, subspace right here, right? So these are three important spaces associated to a matrix. And at the end of this video, we'll see the relation between them. Okay? So basically we just need to remember the definition, right? And row space are in Rn. This is subspace of Rn. Column space is the subspace of Rm, and null space is subspace of Rn. And you would think, yeah, so what happened between row space and column space, because they are in the same Rn, right? We'll see that at the end of the video. Okay, so let's consider the following example. You have matrix A, let's say 0, 1, negative 1, negative 2, 3, and 4. This is 2 by 3 matrix. So the row space is a subspace in R3, right? While the column space is a subspace in R2. Okay. Let's find the basics of the column space and the row space. So basically, you need to find linearly independent subsets, right, of rows and columns. That's it. Okay, let's talk about row space. So the row space, you have two rows, 0, 1, negative 1, negative 2, 3, 4. It's obvious that these two rows are linearly independent, right? So actually this is basics for the row space. So we don't have to do anything else, right? We just pick two vectors in here, 0, 1 and negative 1. The second one is negative 2, 3, and 4. And all vectors in the row space is linear combination of these two vectors. And of course, the dimension of the row space in this case is 2, right? I can write here, dim of the row space is equal to 2. Okay, now let's talk about column space. We have 3 columns. I have 3 vectors, 0, negative 2, 1, 3, and negative 1 and 4. Is that correct? And I think we still remember the problem, how to find the dimension of the subspace generated by these vectors. So basically, we write this vector is in the column form, right? And then from here, we pick vectors which are linearly independent. Since we have 3 vectors in R2, these 3 vectors are linearly dependent, right? Because the number of vectors is bigger than the dimension of the space R2. Does that make sense? And of course, from here we may pick 2 vectors like this, the first one and the second one, because this is some kind of row echelon form. So we pick 2 vectors, 0 and negative 2, and 1, 3. They are associated to leading elements. The first one is negative 2, the second one is n, and they are linearly independent, right? Linearly independent, and I form a basics for the column space. All right, so I think we are done, right, with the row space and column space. And of course, from here we have dimension of the column of A is equal to 2. Okay, so you can see the dimension of the column space and the row space are the same. Is that correct? It's equal to 2. Actually, this comes from here. You can see from here. We have 2 columns which are linearly independent, right? At the same time, you might pick, rows in here, right? They are also linearly independent because, this is the row echelon form. So the dimensions of row space and column space are the same. All right, now let's talk about the null space. The null space of A, that is the solution set of Ax equal to 0. So that means we have to solve this. We have to solve the homogeneous system where A is the coefficient matrix, right? So let's do that. I have, I can interchange. I have negative 2, 3, and 4 in here. I have 0, 1, and negative 1. If you want, you can write 0, 0 in here, but that is not necessary. So I need to get the reduced row echelon form. I multiply the second row by negative 3 and add to the first. I have negative 2, 0, 7, here is 0, 0, 1, negative 1, and 0. So this is the row echelon form And that's not only the row, the reduced row echelon form. And we know that we have two non-zero rows, right? Why? We have three columns. So that means one variable would play the role of parameter. Does that make sense? So from here, I have, suppose that I have x, I have y, and I have z in here. Then from the first equation, I have negative 2x plus 7z equal to 0. And y minus z equal to 0. From here I get x equal to 7 z over 2 and y equal to z. Then you can write the general solution of this homogeneous system as, I can write here this equal 7z over 2 z and z. You see? And if you take z out, you have 7 over 2, 1 and 1. So the null space of A is generated only by one vector. And that is the basics for the null space, right? This is the basics. Why? The dimension of this null space is equal to 1. Okay? So before we move to the next example, I would like to mention one thing, right? The null space is in, the null space of A is a subspace in R3, right? And the row space is also a subspace in R3. Does that make sense? And what can you say about the dimensions of the null and the row spaces? The dimension of this guy is what? Is 1. While the dimension of row is 2. So if you sum them up, you get 1 plus 2 is equal to 3. That is the dimension of the whole space. Something interesting, right? So in the previous example, we don't do anything with the matrix A because the matrix A is already row echelon form. Does that make sense? So now we have a bigger matrix. The size of this guy is 5 by 4. So we have 5 rows and 4 columns. That means the row space of A, is a subspace in R4, and the column space of A is a subspace in R5. Okay, we don't know about the null space, but we'll figure it out. So again, in order to find the basics for the column space and row space, we need to do row elementary operations because you have vectors, rows, right? And then columns. That is the only way, to find linearly independent sets of, from rows and columns. Does that make sense? So I need to make a row echelon form. That is enough for row and columns, but for the null space, we would need the reduced row echelon form. So let's make the reduced row echelon form right away. But I have to mention in here, right? For the row and columns, we need the row echelon form. But for the null space, we need the reduce. Okay, don't forget that. So let's make the reduce right away. It takes a little time, but we have to do that at least one time. So I fix the first one. I multiply the first one with 3 and add to the third, right? And then I multiply with negative 3, add to the fourth, and multiply that with negative 2, add to the fifth. Okay, so I have the following matrix: 1, 3, 1, 3. I have 0, 1, 1, 0, 0. 3 with 3 is 9, so I get 9 here. 3 with 1 is 3, with 6 is 9. 3 with 3 is 9. 9 minus 1 is 8. That is the third row. The fourth row is 0. 3 with negative 3 is negative 9. Plus 4 is negative 5. 3 with 1 is negative 3. 1 is negative 3. With negative 2 is negative 5. And then 3 with negative 3 is negative 9. Plus 1 is negative 8. Okay. And then you multiply that with the negative 2, the first row with negative 2. Add to the last row, I get 0 in here. Negative 2 with 3 is negative 6. Negative 2 with 1 is negative 2. Minus 4 is negative 6. Negative 2 with 3 is negative 6. Minus 2 is negative 8. Right? Now, you multiply, you can see you have 8a, 1 in here, 8a, negative 5, negative 6, right? So basically you multiply the second row by negative 9, you add to this, right? And then you multiply with 5, you add to this. You multiply this with the 6, you add to this. You have very nice form as follows. You have 1 in here, 3, 1, 3. I have 0, 1, 1, 0. As 0, 0, 0. With 8 is the same because you don't do anything with 0. So you get 0 in here, 0, 0, 8, 0, 0, 0. Oh, negative 8, sorry, with negative 8. You see? And of course, these 3 rows are the same because they are, just scalar multiple. So I just add the third row to the fifth and the fourth. I will have the following form. So I have 1, 3, 1, 3. Let's make this longer. Okay. And what's the next? 0, 1, 1, 0. 0, 0, 0. I divide the third row by 8 and get 0, 0, 0, 0, 0, 0, 0, 0. Looks good, right? But that is still not the reduced row echelon form. So for the reduced, I need to multiply this by negative 3, add to the first, and the second by negative 1, add to the first. Right? There's 1 in here, 1 in here. So, okay, so let's do this. I keep the second and the third. So I have 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. Okay, and then here I have 1. Negative 1, I have 2 in here, I have 0 in here, and I get 0 in here. So I think that is not reduced. I think I do something not interesting here. So I think we need to multiply by negative 3, right? Because that is the leading element. I'm sorry for that. But now, okay, let's find multiply by negative 2, add to that. Okay, so we do that twice. Oh my goodness. So I get 1, 0, negative 2, so I have negative 2 in here, 0. I think it's correct. Yes. Yes. In here I get 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. Okay, we have reduced row echelon form. Perfect. Now look at this. That is reduced row echelon form. We have leading element 1, 1, and 1 in here. So, we circle them. Okay. Here we face some questions. The first question. Now we choose, we use we use row elementary operations, right? So do we change the row space using row elementary operation? That is the first question. Because you it's obvious that the first three rows, right? This row, this row, and this row are linearly independent. Is that correct? So can we choose them as a basics for the row space or not? If elementary row elementary operations change the row space, so we don't have a right to do that. But if the elementary operations, row elementary operations, do not change the row space, yes, we may choose these three rows to form a basics for the row space. Does that make sense? Fortunately, the answer for this question is no. Row elementary operations don't change the row space, because when we do row elementary operations, we only use linear combinations of rows. That means we are still in the space generated by rows. Does that make sense? So we will not change the row space. That is very important. Okay, let me explain here, because row elementary operations, we only use linear combinations, right, of rows. So that means we are still in the row space. We are good. Does that make sense? So from here I can do conclusion that a basics for the row space of A is three vectors in here: 1 0, negative 2 0, the second one 0 1 1 0, and the last one is 0 0 0 and 1. And of course the dimension of the row space is 3. So we are done with the row space. Of course, we may choose the original rows corresponding to these three rows. That means you may pick these three rows right here: the first row, the second row, and the third row. They should be linearly independent, because at the end of this, three corresponding vectors are linearly independent. You see this? So the original should be linearly independent. That's it. Okay, now let's talk about columns. How about column space? You have three leading elements in here, and for this you have three columns. The first column right here, the second column's right here, and the third column's right here. So we face a similar question: do we change the column space using row elementary operations? The answer is yes. The answer is yes, because what when you do row operations, you don't change the row space, but columns are changing, right? For each time when you apply that, you get a new column space. Column space of a new matrix. Does that make sense? So basically, yeah, you change the column space, but the columns corresponding to these leading elements, the columns, the original columns corresponding to these leading elements, means these three columns, the first one, the second one, and the last one, they will form a basics for the column space. But you have to pick the original vectors. Does that make sense? So for the column space, I have the following, but I have to mention: row elementary operations change the column space. Okay, column space. Don't forget that. So we may pick vectors to form a basics for column space. Those vectors are corresponding to this leading element. I repeat again, right? Corresponding to this leading element. So the first vector is 1, 0, -3, 3 and 2. The second one is the second one is 3, 1, 0, 4 and 0. And the last one is 3, 0, -1, 1 and -2. And of course, that will be linearly independent. Because if you want to check that, you do almost the same thing, right? You write them, you just ignore the third row in here. You just ignore the third row in here. And you use, row elementary operation to get, the form, the reduced row echelon form, even not reduced, right, for row and column. But you can see that actually these three vectors are linearly independent. Does that make sense? So they form a basics for the column space. Don't forget, we need to pick the original vectors. Okay, I write here original columns. While for rows, we may pick the rows in the reduced or row echelon form. Okay, now let's talk about the null space. That means we need to solve the homogeneous system, right? So I think I need to make a copy of this matrix. Let me copy this matrix. And then we'll find the null space at the end. All right, so I have this. Now let's work with the null space. I need to solve this system, right? Let's say this is x1, this is x2, this is x3, and this is x4. So from the third equation, I have x4 equal to 0, right? From the second one, I have x2 plus x3 equal to 0. And from the very first one in here, I write equation right here. I have x1 minus 2x3 equal to 0. So it's obvious that x3 will be parameter. So I have x1 is 2x3. From here I get x2 is negative x3, x3 is 3, and x4 is 0. Then the general solution looks like this: 2x3, negative x3, x3, and 0. Right? And if you take x3 out, you get x3, 2, negative 1, 1, and 0. So basics for the null space contains only one vector. That is basics for the null space. And the dimension of the null space is 1. Does that make sense? Of course, we can find dimension of the null space once we know the dimension of the row space and column space, because we know that exactly, right? Dimension of the null space is equal to the number of variables or the number of columns subtract by the dimension of the columns, right? So the dimension of row and column space are 3. That means dimension of the null space is just 4 minus 1 is 3. 4 minus 3 is 1. Does that make sense? Let me summarize that theorem, right? As follow. So this is theorem, and this is very important theorem. You have matrix A, that is m by n matrix. Okay. Then the dimension of the null space plus the dimension of the column space of A is equal to the number of columns. In this case, is equal to n. Alright, and the dimension of the null space sometimes is called the nullity of A. Okay, and the dimension of the column n, the row space, in this case they are equal, is called the rank of A. So this identity says the nullity of A plus the rank of A is equal to n. And the rank of A is very important quantity. Okay, so in the next video we will study the rank of A and the solution set of some system of linear equations. The rank of the it depends on the rank of the coefficient matrix and the rank of the augmented matrix. So I think I finished my video in here. We have not many examples, but I think with 2 examples we figured out how to find the basics for 3 spaces associated to a matrix, that is the row space, column space, and the null space, and from there we can find dimension of those subspaces. Okay, so if you have any questions, please feel free to let me know, and see you in the next video.